Alright guys, in this video I'm going to show you how to multiply and divide exponents. What's really important for understanding this lesson is that you pay close attention to the rules that I'm going to show you, but before I explain the rule I want to show you I guess kind of the long version so that you can understand the rule first, and then I will make it simpler and show you the kind of shortcut. So basically what we are doing here is you're multiplying or dividing powers or exponents that have the same base. So that's really important that you understand that they have to have the same base for these things, what I'm going to show you, to be able to be true. So what I mean by the same base for this first example is like 3 squared times 3 to the third. Both of these exponents have a base of 3. If they didn't both have a base of 3, then this wouldn't apply. The exponents, the powers can be different, but the bases have to be the same. So how would I simplify this? Well, 3 squared is, as you can see over here in the expanded form, is 3 times 3, which we know is 9. And then 3 to the third power is the same thing as 3 times 3 times 3. So if I expanded this all out, you would end up with 3 times 3 times 3 times 3 times 3, which in shorter form is also known as 3 to the fifth power. And now you could evaluate that as well, but for our purposes today, we don't actually need to evaluate what 3 to the fifth power is. I just want to show you how I can get this simplified exponential form. So let's do another example first. So this is 7 times 7 to the fifth power. Remember, 7 with no exponent has a power of 1. So 7 to the first power is just 7. And then times 7 to the fifth is 7 times 7 times 7 times 7 times 7, which, if I write that in exponential form, would be 7 to the sixth power. Let's try one more multiplication. Y to the third times y to the first. Again, this works also with letters, not just numbers. So y to the third is y times y times y times y to the first is just y, and then we could combine that into y to the fourth power. So that's those are a couple examples for multiplication. I don't know if you noticed a pattern at all or not, but what I want to show you is that if you look at the original problem on the left here, and you look at the final answer in exponential form, we can skip this middle column if we just recognize the pattern that our final exponent is just the two exponents added together. So 3 to the second times 3 to the third is 3 to the fifth, which 2 plus 3 equals 5. So that's a little shortcut for you, which we'll recap in a second. But just to double check, it works for all of them. 7 to the first times 7 to the fifth, 1 plus 5 equals 7 to the sixth. And then y to the third times y to the first, 3 plus 1 is 4, and that's what we had gotten for our answer. So I'm going to just jump forward for a second here. When multiplying powers with the same base, a little shortcut is that we can just add the exponents, and that is your rule for multiplying powers with the same base. So let's go back to the division. Now you might be able to make a little bit of a prediction about what might happen here, since when we multiply powers with the same base, we add the exponents. What do you think will happen when we divide powers with the same base? So dividing is a little bit trickier to show, so I'll show you how this works. I kind of modeled one already. The original problem here is 2 to the fifth divided by 2 to the second. a little bit easier to see if I write it as a big fraction. So 2 to the 5th on top is 2 times 2 times 2 times 2 times 2 over 2 squared on the bottom, which is 2 times 2. Now you can see for this first one I already modeled, I crossed out these 2's. That's because 2 divided by 2 is 1, so they cancel each other out. And then I have another set of 2's, one on top, one on the bottom, that I can cancel out. And then what's left, 2 times 2 times 2, is my answer, which would be 2 to the 3rd. So let's try another one the long way first before we look at the shortcut. So 4 to the 6th, that's 4 times 4 times 4 times 4 times 4 times 4, all over 4 to the 5th, which is 4 times 4 times 4 times 4 times 4. So what we're going to do is we're going to find as many pairs of 4 over 4s as we can, because they all cancel. 4 divided by 4 is 1. 4 divided by 4, that's cancels, that's 1. 4 divided by 4, 4 divided by 4, 4 divided by 4. There's only one left, which is 4 to the 1st power, or you could just leave it as 4. And then again, we can do the same thing with variables. So g to the 5th is g times g times g times g, all over g, which is g to the 1st. Cross out g divided by g, because those equal 1. No matter what g is, it could be 1 million. G divided by g is always 1. So it could be a million over a million, and that's still 1. And then what's left is g times g times g times g, which is g to the 4th power. Okay, so again, if you hadn't found a shortcut yet, let's take a look. So this first example, we had 2 to the 5th divided by 2 to the 2nd, and we ended up with 2 to the 3rd. So you can see 5 minus 2 equals 3, which is our exponent in our answer. Let's look at the second one. We started with 4 to the 6th, divided that by 4 to the 5th. That is 4 to the 1st, which is 6 minus 5 is 1. And the last one, remember, g to the 5th divided by g to the 1st. 5 minus 1 is 4, which is what we had for our answer. So, to recap, when we multiply powers with the same base, we add the exponents, and when we divide powers with the same base, we subtract the exponents. So just a couple quick examples down here at the bottom. Without having to expand, these are much easier now that we know that shortcut, because it would take a long time to write x to the 20th power and x to the 40th power. So all we have to do is add 20 plus 40, which is 60. And then same with this one, 5 to the 75th power. That would take a long time to expand. So it's a lot easier now that we know the shortcut. 5 to the 75th divided by 5 to the 20th is 5 to the 55th power. All right, I'm just going to show you a few more examples like the ones we just did, but these ones are, some of them are a little bit more difficult, so I'm going to walk through a few additional examples. So here's our rule. For every non-zero number a and integers m and n, a to the m times a to the n equals a to the m plus n. A lot of times in math we show rules by using letters to replace all numbers, and then we use a little description to explain what those letters can stand for. So basically this is just saying a can't be 0, and then m and n can be any integer. All right, so a couple examples, 11 to the 4th times 11 to the 3rd. Using the shortcut, you would add 4 plus 3, and that's 11 to the 7. Okay, this one down here is a little trickier because we have a negative exponent, which we didn't talk too much about, but we have the same strategy. Is 7 to the negative 3rd plus 7 to the 2nd, and 7 to the 6th. So you're actually going to add negative 3 plus 2, which is negative 1, and then negative 1 plus 6, which is 5. So your final answer here would be 7 to the 5th power. Okay, this one is a little bit tricky. If we notice, we have some coefficients here, 2 times 3. What this means is you're actually going to just multiply the coefficients, and then you're going to multiply the bases, the exponents that have the same base. So 2 times 3 is 6, and then n to the 5th times n to the negative 2nd. Remember, we're just going to add those. 5 plus negative 2 is 3. So here's your final answer, 6n to the 3rd. All right, looking at this next example, you see we have two different variables, x and y. So what I like to do is, because you can only combine the powers when the bases are the same, I like to put the bases, the x's and the y's together first, just so it is a little bit easier. So I will put the 8, x to the negative 8, and the x to the 2 together, and then I will put the y squared and the y to the negative 1 together. You can do this because this is all multiplication. Remember, when everything is multiplication, you can move things around. It's called the commutative property. So I'm allowed to do this because it's all multiplication. Now that I have my two x terms together, I can just simplify these. So x to the negative 8 times x to the 2nd. Remember, since we're multiplying these two powers and they both have a base of x, I will just add negative 8 plus 2, which is negative 6, and then y to the 2nd times y to the negative 1st. They both have the same base, so I can just add my exponents. 2 plus negative 1, which is 1. So my answer is x to the negative 6 times y to the 1st. And again, you don't have to put the 1 there, you can just write y. All right, let me show you some division examples. Here's the rule that we talked about for division. For every non-zero number a and integers m and n, a to the m divided by a to the n is the same thing as a to the m minus n. So same thing I showed you in the first few table examples that we did. Again, this just means that the a is just showing that the two bases are the same, and that you're going to take the top exponent minus the bottom exponent to simplify. So 3 to the 8th divided by 3 to the 5th, all you have to do is subtract 8 minus 5, and you get 3 to the 3rd power. Here we have a to the 6th divided by a to the 14. We subtract 6 minus 14, and we get an a to the negative 8. Now, sometimes after we do the first few examples, we say, yeah, that makes sense. And then once we start doing the shortcut, we forget, wait, why are we subtracting? So if you forget, again, you can always do the long version to kind of prove. And this will show you, since we didn't really talk much about negative exponents, this will show you a little bit what that actually means. So let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, why did I pick the long one? 11, 12, 13, 14. Okay, so the reason we get negative exponents sometimes is because if I do the long strategy like I showed you at the very beginning of this video, if I cross out all my pairs, a divided by a, until I have none left to match up, you'll see what happens is that the 8 a's that are remaining are all on the bottom. So that's actually what a negative exponent represents, is that there's nothing left on the top, but all 8 a's are on the bottom. So what we could write this as is a to the negative 8, or you could actually write it like this, which you don't have to worry about doing both methods. I just wanted to show you where those negative exponents come from. All right, this is similar to one of the multiplication examples I showed you. The 12 and the 3, those are just coefficients. So those are going to be completely separate from the a to the 6th divided by a. So I like to separate them almost like two separate problems so that you don't get confused. So 12 divided by 3, that's just simply 4. And then a to the 6th divided by a, remember, a lot of times we forget this is a to the first. Don't forget that that's a 1 there. It's not a 0. So 6 minus 1 is a to the 5th power. Okay, and then just like we did in the last one, I like to put the variables together that have the same base so that you don't try to combine things that can't be combined. So m to the first divided by m to the first, this is actually going to be 1 minus 1 is 0, so m to the 0, which we'll talk about in a second, and then n to the 2nd divided by n to the 1st, 2 minus 1 is 1. You could leave it like this, but you might remember from one of our videos at the beginning of exponents, anything to the 0 power is actually 1. So you could actually simplify this a little bit further, 1 times n to the 1st, or actually just n. Because if you notice, m divided by m, that just cancels itself out. Okay, these are just a couple other examples if you want to try them. I'll write the answers in here so you could pause and try them yourself if you want. And that is totally up to you. Otherwise, you can stop the video and get started on the rest of the lesson.